The short block. It's more than just the block. We've got a lot of parts to cover here today. So we're going to have our block itself, the crankshaft, rods, pistons, rings, bearings, balancer, flywheel. Now typically the balancer and the flywheel may or may not be included in the short block. However, I am including them in here for our discussion simply because if you've got an external balance engine, then the balancer and the flywheel need to be considered as an assembly part of the crankshaft. We're going to start with our block. You know, whether you're using a stock block or an aftermarket block, it doesn't matter. That's the entire foundation of your engine build. No, we need to pick whether we're using a stock or an aftermarket block. Number one, based upon what our goals are. If we have a goal of a 500 to 600 horse street engine, then a stock block probably is going to be okay in most applications. But regardless of which it is that you're going to go with, whether it's stock or aftermarket, there's things that need to be correct with the block. And that is going to be the line hone. So that's where our crankshaft rides. So if we got our main caps on our block, we're wanting to make sure that our crankshaft center line, or this bore right here, is the same on all of them, because if they end up, as an exaggeration, you can see these lines are not lined up like that. So that would be like our main saddles are doing like this in the block, or moving around. That's going to take away our bearing clearance because our crankshaft should be straight. And if we've only got 2 thousandths of bearing clearance and the main saddles are off by a thou, well, if one's to the left, one's to the right, or one's up, one's down, a thou, that's our entire bearing clearance of 2 thou gone. And we're going to have problems. So, starting with the main bores, and usually a line hone, that to get that straightened out, that's like step number one on the short block as far as machine work goes. This, obviously after we've checked it for cracks to make sure that we're not having a problem. Where we'd end up line boring, which the line boring would be, we actually either putting aftermarket caps on, or we're cutting the caps a significant amount to lower them down, so the cap gets material cut away. Let me use a different color marker. Yeah. So we would end up cutting a little material off the bottom of the cap right here, which would then move the entire cap down, and then we'd be able to come back in and cut a fresh material bore. Now typically we'd cut just a sliver out of the block side, no more than a thou or two, so that we can have a clean, beautiful round bore again. That way we know everything is in line. Another one with the block, especially if we're talking a V8 block, is going to be square decking. So we've got our block, well, our two decks here should be 90 degrees to each other. Because if we're talking a 45 and a 45, now granted that's not the case for every block, but if we're talking a typical American V8, it's going to be a 90 degree V8. And I've drawn terrible lines here. But square decking not only involves it being 90 degrees from deck to deck, but we're also lining it up based on our main and camshaft center line, so that we can have a perfect 45 degrees on both sides. what that does is it establishes that our crankshaft main center line up to the deck on both sides will be equal, and it will be even end to end. Depending on the type of machine the block was originally machined on, it is not uncommon to be looking at the side of a block and have it have an angle front to back like this. So that's the other thing. We're coming in and we're gonna square deck it. We're gonna make sure that it's flat front to back, as well as being square side to side. Now we jump into our cylinder bores. Usually they're always pretty good on their spacing. However, there are, mismatches because it's just machining tolerances. So if we're cutting the block with a CNC machine, or if you've got a BHJ true fixture block, the it references off of the two dowel pins so that you can, the machinist can indicate the fixture and put these cylinders back exactly on center spacing, because they might have, a couple cylinders too close together, a couple of them too far. They all might be one way or the other. Like, it's hard to tell, so we want to machine them in a way that the spacing is perfectly even and to where it should be stock. So this is also referencing the dowel pins on the decks, depending on how it's done, because that's where the cylinder head goes on, and we want our cylinders lined up with our cylinder head. Now, there is, as always, tolerances to all of that, but if we're going through the work of machining a block, we want to make it as perfect as possible to the way it's supposed to be. Now, this isn't always the case where you can make it perfect unless you're willing to machine on it. To straighten cylinders out, we're always talking about overboring. However, if you've got a block that's really good on the cylinders still, like the crosshatches there, the finish is nice, and the size is good, it's not completely worn out, you're going to have to kind of choose. Do you want to just leave that and skip having to bore and hone the block, or do you want to focus on straightening out? Typically, straightening out and making the block perfect is not going to be worth a noticeable amount of power over something that you already has good cylinders in it. But if you have to bore oversize, typically cylinders are going to be less than 10 thousandths off from factory blueprint. And if you're going to a 30 thou over bore, that's going to be able to be cleaned up by boring to a 30 thousandths oversize and fixing the location so that it is good and you're not losing anything because you're already at the point where you have to bore it oversize anyway. I should also make the point that manufacturing tolerances have come a long way in the last 50 years. So, anything that is an original engine from the prior to the, let's say, early to mid 90s, it's definitely going to have the problems that need to get fixed. I don't know when things really started to transition. I feel like some stuff was late 80s, some stuff was early 90s. Versus, if you're starting with an engine that was built after, say, 2000, a lot of this machining should be a lot better to start with. Most notably is going to be cylinder location and this deck taper. The deck taper was definitely because of the machines they were using back then. There's a certain machine that just was real quick and fast, where you just like flip the block side to side. So the taper would, that they used that machine because the taper was always in opposite directions on the decks. So it was real like a quick and dirty machine to get the job done, but it left a taper. But what that taper did was, lower compression on one end versus the other, and then it's flipped for the opposite deck. That should be much better on any more modern engine, like say an LS or a Coyote or anything like that. However, the main size does still need to be checked, and I haven't worked enough with those new engines to really have an opinion about what the square deck looks like. But I would expect that to be a little better as well nowadays. However, the thing to keep in note is all of this stuff is typically only as good as it can be until it runs. And with the way that a lot of modern engines are just happy to take boost, and people are more than happy to keep cranking it up, the block moves. Like a cylinder block moves. And that is a very difficult thing for people to understand. You know, your mains, you start cramming 1,000 horsepower through a block that was built for 400, guess what? They're gonna get messed up. That's why we got cross-bolted mains now on most of these blocks there, and they still move and get messed up. All of this stuff can get ruined by high horsepower because of the way it stresses and tweaks and moves on a block. There was a great example of this that, I don't even know if I can demonstrate it, but we'll see if I can demonstrate it later. But when I was at school, we had a small block Chevy block sitting on a bench, and you could take an inside micrometer. You could set it so that it would just hang there in the block. So like it's set to the maximum size and it's hanging there in the block. And I think we had it lengthwise with the cylinder. And then you could put your hand on the valley of the block and push, and it would fall out. And that is pushing with your hand. Now, what do you think that block's doing when you're trying to run 4, 5, 6, 7, 800 horsepower through it? There's a hell of a lot more cylinder pressure than there is what your hand is pushing on the valley with. So, things to keep in mind. That's why your block should get checked out by a machine shop, or at least measured with the proper tools at home, to make sure that you don't have any wonky craziness going on, especially with crankshaft. All right, check out the demonstration. Now this is my Oldsmobile diesel block. That's, being a diesel, it's already much beefier than a regular gas version of the block. And I've been running this block in a 520 up to a little bit more horsepower than that application for the last 2 years. It was just a part getting freshened up again. So this is stronger, and you can see I can still deflect the block enough to make this happen. Now that you've seen that, crazy, right? That's also why when all this machine work is happening, especially your cylinders for final honing, torque plates, because that little bit of pushing on the valley, making everything deflect. What do you think your head bolts are doing torqued in at, you know, anywhere from what, 70 to 120 plus foot-pounds, depending on the size of the fastener? Like, it is really stressing those areas where those head bolts are. And a big one where I've seen the largest amount of deflection because of that is a big Cadillac, like a 472 500 Cadillac. The head bolt holes are really close to the cylinders, and when you torque those up, I think I measured a 2.5 thousandths deflection at the top inch of the cylinder from those head bolts. Like, it's a lot. I think on my Oldsmobiles I've typically seen a thou and a half of deflection. You know, even on like an aftermarket Dart small block Chevy block, it still deflects a half a thou to a thousandths. And it's that big reason why you should always be getting your block machined with the torque plate, is because otherwise you're taking that top inch of the cylinder where the most cylinder pressure happens and you're distorting it after the fact and making a leak around your cylinder rings, because now your cylinder's not round anymore at the very top. So it's going from a round cylinder to a tweaked one. It's going to get blow by right there at the top where it's supposed to have the max amount of cylinder pressure. Like, it's just, yeah. Torque plates, make sure you're doing stuff. That's why your mains all everything's gotta be torqued. If you got cross bolted mains, you better have them cross bolts in when the mains are getting done, because same thing. They're pulling on a main cap out here, but it's gonna change the shape of the hole that the crankshaft goes in. And it just, yeah, it's crazy to think how much blocks move and how important good machining and doing it in the right way is to making sure that everything's gonna, you know, still be happy once it's all put together and running. All right, up next is our crankshaft. Now, our crankshaft has a center line, and we've got our main journals along there. Now, you need to check the crankshaft for straight right off the bat. You know, we don't want to have anything like that going on with our center line. If we do, we need to try to straighten the crankshaft out. Oh yeah, and again, Magnaflux crank. You don't want to start trying to put any work into something that's cracked. But yeah, if our crank is bent, we need to straighten that out and bring it from the red line back down to the blue line. The next thing is going to be, you know, what do our journals look like? Are they usable as is? Can they get away with just a small polish? Or do they need to be reground? Now, we've also got our rod throws. And normally these be 90 degrees each other. I'm drawing this like a 4-cylinder crank so that it's easier to visualize. These also need to be, if it's a V8, they're phased 90 degrees to each other. You know, from the center line, you know, so we're gonna have, say, 1 and 2, 3 and 4, 5 and 6, 7, 8, or whatever the spacing is. It's usually, or I think, or whatever, but I don't know, I have to look at a crank. It's hard to visualize right now, but anyway, so on a V8 we'd have, you know, a throw, so we're gonna have 2 cylinders on each throw in a 90 degree, but if they're also, it could be like this 4-cylinder one, if it's a flat plane crank, like there's several different types of crankshafts. You also got ones where they can have an offset rod to them. But the point here is that everything here needs to be phased correctly. So on this V8 one, the big thing is we want, you know, 90 degrees between all of them. And they're not necessarily perfect that way, the way they're manufactured. You know, we could have 90 degrees on one, we could have, you know, an 89 and a 91 or something like that, where, I mean, they're more than close enough to run, but it's not perfect. So again, we're using machine work to make it perfect, or as close to perfect as we can get it. There's also where, you know, this rod here might, let's say it's got a 4.001 stroke to it, and then the next journal down's got a 4.003 stroke, and this one's got a 3.995 stroke, and this one's got the 3.999 stroke. You know, so our strokes are slightly different in all of our cylinders. We'd want to regrind that crank to make sure that we can have a 4.000 stroke on all of them to make sure that they're going to be even as possible. Because the more even we can make every single cylinder burn in the engine, the more smooth it runs, and it will make more power because of that. That this phasing and the stroke length are typically not something that normally gets checked. However, if a crank needs grinding, then the crankshaft grinder, if they're good at their job, is going to be correcting these things as they do it. Because a crank grinding machine has an indicators on the sides where they can turn it a true 90 degrees as they step from journal to journal kind of a thing, as well as having a way to fix the stroke on each end. The only time that this gets into a bit of a, not matching up is if it's something that's super oddball and they're trying to just do a bare minimum cleanup thing. But even with that being the case, typically your bearing undersizes go in 10 thou increments, and 10 thou is usually more than enough. Like this one being 5 short, we need all of our 10 to straighten that back out to center, because we're going to need, if we take 5 and 5, it stays the same. So we basically got to take 10 and none, and we can move that center line, because you need twice as, if you're 5 off, you need 10 to make it right. But typically with crankshaft grinding, now you guys need to know this, but you need about a 2/1000 of all the way around to get a good, nice cleanup finish kind of a thing. So really, if it was that far off, especially, with, well, I guess the other one wouldn't matter. 3 would be fine. But at 5 off, we'd probably need to plan on going to a 20 just to make sure it cleaned up perfectly. Or we make the compromise of, we're going to go for 3.999 for all of the strokes to give us a little bit of cleanup, and we'll have just a little bit of cleanup left on that one too, since it'll be 4 different and 4 different. But that's not something that you should typically ever need to worry about. This is just giving you the information of what actually needs to go into all of this when it's getting worked on. Another thing to look at is the thrust. The thrust can be located on any journal. It depends on what type of engine you're working with for it to be matched up. And the crank thrust surface just has a wider flange area that then, a bearing sits in there on both sides, and that just controls the forward and aft movement of the crankshaft. Pretty typical for this is, I think most manufacturers shoot for around a 7 thou. However, I have to, like 5 to 12 is the typical acceptable range. On anything that I've run into, if I'm at 5 or even below, I'll actually sand on the bearing a little bit. Like typically I'll assemble it, try to spin the crankshaft over a little bit while pushing it one way and just get a little shine so I can see high spots. And if there's clearly high spots, and the reason why you might end up having to do that is if the main cap isn't sitting totally square. So like we were talking about on the block side, we got block on one side, main cap on the other. Well, if the main cap has a lean to it, it's going to pinch on one side of that thrust, and that's not any good. And at that point, if you're already at the assembly phase and checking this clearance, it's a lot easier to just do a little bit of filing or sanding on the bearing to make sure you get the clearance right than to turn all back around and start over because the cap's a little crooked. And This is obviously an extreme situation. That cap, typically they're about 1 inch wide on the bottom, give or take, as far as where it mates up to the block. However, at even just a slight degree, and by slight I mean 1 degree is 1 degree equals 17 4 thousandths. So 17 thousandths 4 tenths per inch. So if our cap's about 1 inch, 17 4, like that is an ungodly big amount to screw up a main cap. You know, more typically is if a main cap's going to be slightly off, it'll be off by, say, 1 thou, maybe 2. Now, I say I've seen factory ones that were at least 2, 2.5. So typically you grind the side of the cap, grind it square. But again, things you don't need to worry about. Your machinist should be taking care of all this stuff when it happens. So we're just talking about an ever so slight difference. However, if the factory had it screwed up bad enough and then your machinist straightened the cap out, the factory cut the thrust face on the cap after it was already crooked, and then you might run into a situation like this and you can just, like I said, sand or file off the high spot a little bit and it will run perfectly. No need to worry about it. Once your crankshaft work is taken care of, you know, that's making sure that all this stuff is straight, everything fits nice, kind of a thing. You're also, this is when you need to be starting to think about your bearing clearances when you're grinding your crankshaft, because like I said, they're typically 10, 20, 30. You know, if you got something super common, you can get 9s and 11s, you know, or even if it's, you know, talking standard, you can get what's an X, and X equals 1 thou extra. So it's actually kind of like a -1, you know, versus a +1 kind of thing. You also get +1s to tighten it up. We'll dive more into this when we get to the bearing oil systems and bearing clearances. But you do need to start thinking about this type of stuff if you're sending your crankshaft out to get reground, because if you're in an application where, say, factory spec is 1 to 2.5 thousandths oil clearance, and you set your block at center of spec, you set the crank at center of spec, and your bearings are perfect, which, you know, that can be a whole thing too. You know, you're going to end up with, let's see, what would that be? Say 175. You know, so 1,007 to 8. That's really tight for a high performance application unless all your components are designed around it and you're using the right weight oil to make that work. If you're using a stock crankshaft and have that kind of clearance on something that you're building for performance, probably not going to fly. You'd probably be way better off being at the 2.5 size for your mains, and maybe even the rods, depending on, again, you know, what you're using for components, that you're going to need that extra clearance. Well, if you go to the big side on your block, there's probably 4 to 5 tenths there, so half a thou. You know, that only gets us part of the way there. You know, you can work the rest of it out with the crankshaft sizing. You know, or you can specifically ask that your mains or rods be made to a specific size so that you can set the bearing clearances that you want. All right, up next is our connecting rods. Now, much like the block, in order to recondition them, typically come in, we're going to cut a little material off the cap, a little bit off the rods, just to make sure everything's squared up. And by squared up, I mean if we're looking at it from the end, we're going to cut this surface square to one of the sides. That way we know that we're cutting it square and we're not influencing and putting weird funky angles on anything. So you'd clamp it down and then run your grinder across it. Again, it shouldn't be anything you have to worry about. Your machinist will do it. So what this does is it shrinks this hole, and then we hone it back to size to make sure that it is round, or as close to round as we can get. That's one thing that they don't want to really talk about, is when you're reconditioning a connecting rod, it's always going to be big at the parting line. So our parting line being this part right here. So when it comes together, you know, what we're going to have for a size this way is not going to match this way, because it will be longer pointing at the parting lines than it will be top to bottom. And that is fine, because your bearings are shaped the same way. We put our bearings in here, and they do the same thing. Your bearing is a little bit thinner at the parting line than it is at the bottom. And the reason for this is when your connecting rod is cycling up and down in the engine, your forces are pulling and compressing. And the big one being when your cylinder fires and it's pushing down, it's pushing against the cap, that's pulling on the bolts, and the bolts are pulling it, and it's kind of squishing this all together, so it's pinching the sides in. So your bearings are shaped in a way that they have extra clearance there because they know it's going to pinch. And that's why it's also okay when you recondition a rod, it's going to end up big towards the parting line, as long as we've got basically from about here over to about here in size, nice and round. That's what I've been happy with. If it's getting any further past that, it's really where it might be kind of an issue. This is also why when I measure bearing clearances, we're going to measure top to bottom, and then at like 30-degree angles or 45-degree angles on each side, we're going to take the average of the two 45s and then average that with the up and down in order to get what I call a true readable rod bearing clearance. There's also some measuring devices you can use that are three-way kind of a thing. So you put them in the board just like this, and it's going to average it for you basically, where you're measuring the two diagonals and the vertical all averaged together. I've compared the two. I've done this way with a typical two-side bore gauge and versus the three-side one, and we're talking about a 1/10 or 2/10 variation, more than close enough for really wanting to dial in and know where we're at. But that's getting ahead of ourselves again. We'll save more of that for bearing clearances. Along with the connecting rods, if we're doing anything with the pin side, if there's a bushing in here that needs to be replaced and resized, that'll get done. Not always the case. It's just on like a floating application, there'll be a bronze bushing in there that'll need to get might need to be replaced if they're used rods. If they're new, you shouldn't have to worry about it. This hole might get honed out if you're trying to convert a stock rod from press fit to a floating. It's just going to be a couple of thousandths that come out of there so that the wrist pin will slip. If you're changing your bearings, if you're changing your bolts, then for sure you need to recondition your connecting rods. And the reason here is that when you stick your bolt in, and they're torqued differently. That is going to compress the top of your cap here. It's going to pull on the connecting rod portion. It's going to pull these together harder, which is going to distort this bore. And that's really going to be, you know, if you're talking stock connector rod, like a 20 something or 30 foot-pounds versus putting in a high-grade aftermarket ARP. If you're doing the stretch method, it could be as high as 100 foot-pounds that fastener is being torqued to, and that's definitely going to change the shape of this bore. Just like it's going to change the shape of the bore for our cylinder bores from our head bolt torque, or our mains from our mains on our block also. This also goes for if you're putting studs or different bolts into your main bores. Like, you need to, at the bare minimum, check to see how much they distorted and whether it's acceptable or not. You know, typically I'd say you should almost always be putting studs into the block and putting higher grade bolts into your connecting rods. But they will need to be resized because this bore is going to get tweaked with the different torque specs. All right, now for connecting rods, we've got H-beam and I-beam are typically what they're considered. Most factory style stuff is what's considered an I-beam. Most aftermarket stuff is an H-beam, and all that's referring to is what this portion of the connecting rod kind of looks like. Let's see if I got some examples here. Oh, never mind, the things have been laying around dirty, but you can see this style with the way that beam is shaped. It's got a deep recess on the side, you know, probably about like that where these comes out. So this one's referred as an H-beam because if you looked at it from the end, it's going to look like an H. And a stock rod would be much shallower if it had any of these sides at all. So, you know, the center part here is what's much wider and thicker, and then that's why that one's called an I-beam. If they're not just totally flush anyway, in which case then it's just not even really referred to as anything, but H and I would be what the aftermarket labels them as for a difference. So if I want to draw that out, you know, if you were to cut it in half, you know, an H is probably kind of more like that versus an I-beam would probably look more like that if you cut it. So most aftermarket rods are going to be an H-beam style. There are a few like ultra high-end big boost application ones that go to the I-beam style, but typically it'll be an H-beam is the most common style. I mean, again, like I said, a high boost application, it might be an I-beam style. The difference is literally just more based on application than one inherently being better than the other. Typically the H-beam, you can make it stronger while being lighter weight. That's what the big difference there, and that's why most of them end up that way. Pistons. They come in all shapes, sizes. It's kind of limitless what can be done with a piston. There are several types. There's an oversimplification here. We've got flat top, dished, and domed. Now, one thing to point out is that these are typically chosen based on the compression ratio they can provide. Now, in a theoretical world where if we could keep every everything about the engine the same, but put all 3 of these style pistons in and do testing, the disc piston will make the most power. The reason for that is because as you have cylinder pressure pushing down during the combustion cycle, it's kind of collecting it and moving it in to push on the piston and just the piston, versus the dome is like trying to shed it, and it puts it into the gap to your cylinder wall. So it's kind of pushing it down onto the rings and with more collected pressure, if you will. Although we're talking small stuff if you can actually measure it. Where if your ring gap is there, it's gonna leak through your ring gap. But largely, that's not even worth worrying about for 99.9% of the people out there. So you're just choosing a dome, flat top, or dish based on the compression ratio you're trying to achieve. Dish being lower compression, dome being higher compression. In most typical street applications kind of a thing, we're going to have a flat top or a small dish. Now when it comes to the piston, we've got a couple of different measurements to talk about. Number one, bore size. It's pretty obvious. So that's your cylinder that the piston goes in. The piston skirt itself is going to actually be tapered. So if the top of the piston's up here, it's actually going to be kind of angled like this. Where typically where the piston, if it's coming down and it's got a skirt off the side, the skirts are where it's going to be widest. That's why when you measure a piston, you only measure it across the skirts. When we're looking at bore size versus piston, the clearance is in the piston. So if we got a 4-inch bore and we order pistons for a 4-inch bore, the piston is probably going to measure 3.995 and it'll have 5 thou clearance down here on the piston skirt. It will actually be several thou smaller up at the top, and the reason for this is because all your combustion heat is up here at the top of the piston. So when that piston gets hot, it's expanding at the top more than the bottom, and that squares it up in the cylinder. Pistons are also not round. They're definitely more of a oval shape. And again, this is due to thermal expansion because you got long skirts on one side, and then you've got your wrist pin going across. So there's, if you're looking at it from the top, it should be, so this would be the sides with the skirts. Well, I shouldn't have drawn it like that, but you'll have your skirts. And your wrist pin bore will be going across. And then if we were looking at the bottom side of the piston, it's going to have a lot more, structural reinforcement in these areas, kind of a thing. So there's a lot more meat in here, and as that heats up, that's going to expand as well and end up filling in these areas. I believe some piston manufacturers talk about that as being, I think they refer to it as the cam profile of the piston. And all about designing a better piston is about designing the piston to be round when it's hot and operating at temperature going up and down the cylinder, not for it to be round on the bench. Also, our flat top down to the center of our pin is our compression height. This is the same on all pistons, regardless of whether it's a dome or a dish. A dish will actually typically have a little bit of flat right at the edge. Same thing with a dome, it'll have a little bit of flat right at the edge, and mostly that, unless it's a Hemi, you have some cylinder flat sticking out somewhere on that cylinder where, you know, if you're looking at the crown of the piston, you know, you might have 2 valve release like that. You know, if it's a flat top, these will be small recessed areas for the valve relief. And all of this up here will typically be flat, as well as, you know, a little bit around the edge. If it's a dome, it'll probably be raised in some of that area, you know, or if it's a dish, it'll be low in that area, plus over here as well, kind of a thing. But there's always somewhere that's flat. That is where you measure your compression height, which is center of the wrist pin to the top of the piston, which is what we're lining up with the deck of our block if it's 0 deck kind of a thing. And 0 deck is just referring to our cylinder block and our piston at top dead center are exactly the same height, would be a 0 deck. Now there's also multiple different materials and types of pistons that you can get. You know, we've got cast pistons, forged, which then have different alloys available. Can't remember what they are right off the top of my head, but there's slightly different alloys for slightly different applications. I have never really put too much thought into which type of alloy, just because a forged piston is so much better than a cast piston for a performance application that the type of alloy is where you're starting to split hairs. Like, I'm sure there's going to be an engineer that watches this that wants to argue about it, and I really just don't care. It doesn't matter to me. It doesn't matter to 99% of the people out there which alloy it is. And just, you know, if you want to look into the reasons why and make a choice based on that, you can go right ahead. The difference that you'll run into is the expansion rates are a little different. And even from the cast, which is where we're talking about where this piston changes shape. However, that is not something you as the person putting the build together needs to worry about, because the clearance is in the piston. You do not need to be buying pistons, measuring them, and then honing the block to fit each individual piston. That is just silly and wrong. And I have done it before with really poorly manufactured piston tolerances. There's one brand in particular I've run into this. I don't want to call them out because maybe they've got their shit together lately. But you should be able to pull a set of pistons out of a box, measure across all of the skirts, and they should all be very consistent within a few tenths. And if you're buying proper aftermarket forged pistons, they're going to come with a spec on what the clearance should be. It should make absolute sense for it to be to whatever bore size you ordered it for. That being said, when a block is getting honed, you can add a little extra for some safety margin. You know, you can put it right to 0 on your number. You can go plus a half a thou for maybe like a street application. You can go plus a thou for maybe more of a race application. However, depending on if you are going to be the type of customer, you can make it to, it can go to 0 and you can make a little extra power. However, if you're doing that as a race application and you're going to go to the bare minimum on piston clearance, that engine better be fully up to operating temperature, and it better have good cooling that keeps the entire block consistent on temperature so that you don't wear out the piston skirts. Otherwise, add a half to be a little safe for street application, add a thou to be a little safe for a race application. The amount of cylinder leak down that you're going to change over that thou is not, it's not nothing, but it's a hell of a lot better than scuffing the skirts off your pistons and taking out an engine because you started it cold and went ham and ruined your pistons. Alright, our piston rings. Much like our pistons, they come in all kinds of different sizes, shapes, and flavors. Typically, you're going to have a top ring, a second ring, and an oil ring. Now, the top, that's the one that's doing the sealing of your compression. The second is actually more oil control than compression. I think last time I saw like some figures, they figure it's like 20% compression sealing and 80% oil control. And then of course our oil ring is all about trying to control the oil. Now inside of our piston, we've got our grooves. They're open to the face, so our oil ring is typically going to be a top band, bottom band, and then like a spring ring in there that helps keep it tensioned to the outside. We also need to worry about our gaps, which are gaps is when it's in a cylinder, we're going to have our ring is not going to connect, and that is our gap. Typical oil ring is going to be a 15 thou minimum. As long as you can get a 15 thou feeler gauge in there, no problem. Your top and your second rings are going to be based off of the application, the bore size, and the type of ring itself. That is information that will come with your ring pack, especially if you're getting quality stuff from like Total Seal. There's a little pamphlet that'll come with it. Actually, I think I have one here somewhere. Yeah, whatever. I'm not going to dig it out. Well, first it's a pile of stuff. But anyway, just for argument's sake here, let's say that, yeah, what is it? Trying to go off the top of my head. Let's just say the top ring's gonna be like 6.5 thousandths per bore times bore, and your second might be 4.5 times bore. But these numbers will go up or down based on the application. You know, nitrous, boost, all that's going to make the gap need to be bigger versus if it's, if it's like a marine application where the block is always cold and everything runs cool, that might make it go up, I think, as well. Because then the disparity between the block and the piston is more. But otherwise, if it's a street application that doesn't see a lot of power or is always going to be warm kind of thing, that can get tightened up. But all this is referring to is setting what our minimum ring gap needs to be, because if this gap goes away, especially on a top or a second ring, it pinches tight in the cylinder. That's when you snap off the top of the piston. You can ask some Subaru people about that, because it happens from the factory quite a bit. At least when people start messing with them and cranking them up. So that's because they're using factory gap stuff and they added power and they didn't open up the ring clearances to work that way. And pinch them together and snap the crown piston off. Now our second ring can have a couple of different shapes. I think we'll go with the fancy one, like our oil ring here. And this is with the cylinder wall on this side. We'll switch sides here. So I've got a cylinder wall on this side. The second ring can come out and it'll have like a taper down, kind of like that to scrape. There's also a version that'll come out. It's a little more flat face, but then it's got like a little hook on it. That one's referred to as I think a Napier ring. So what that's doing is kind of like scooping the oil off of the cylinder wall. For our top ring, I think the most common is a barrel face. So it's just got like a rounded barrel edge to it. It can also be a taper, like the opposite of the first, second ring. And then either one of those, like there's gapless, where it's like two rings linked together. So like they got gaps. They're just like located opposite, but they interlock to each other. And again, it all depends on, there's different rings for different types of applications, and that each, makes one better or worse for a certain type of application. So if you're really trying to science it out, there's a lot of stuff there to choose from. I'd say the most typical for a high performance application is going to be like a barrel faced tool steel top ring and a Napier second ring, just as a general all-arounder kind of a choice. There's also a clearance between the ring and the top and bottom of its groove, as well as the inside of the groove. You always want to make sure that when you fit a set of rings, you can flip it over the other way and stick it into the piston. So if we got our piston there, here on the bore side. So if we got our piston, and then it's got its bottom of that groove, you want to take your oil ring and stick it in there and make sure that when it's bottomed out, it's below the edge of the piston. Because if it's too tall, it'll bottom in the groove and jam against your cylinder wall. And that's a real good way to wreck stuff right off the bat. That's not good either, so that's a good check to always do when you're putting stuff together. Do that for the top ring, the second ring, the oil ring. Now, it was talking about the oil ring and the second ring also controlling oil. The first oil ring has a bunch of ports off the back side that might go up to the wrist pin, or they're going to the bottom of the piston. So it's like catching the oil and driving it somewhere. It's almost, think of it almost kind of like an oil pump for wrist pin cooling or cylinder cooling, or piston cooling rather. So that's redirecting the oil in there. Your second ring is just trying to redirect the oil and keep it along the cylinder wall and not let all of that oil get up here and get into your combustion chamber, spoiling your combustion. Now when combustion happens, and we've got our ring versus our piston, so our ring is going to be out sealed against the cylinder wall and combustion is happening. So that combustion pressure is coming down. It's going to get down in that groove between the cylinder wall and the piston. So we've got our cylinder wall out here. And it starts pushing down. But it's also going to push in here and push down, and then it's going to push on the backside of the ring. So our combustion pressure is actually being used to push our ring into the cylinder wall to seal it, as well as down onto the bottom of the piston to seal in that area. And once that's all sealed, that's when we get our drive pushing down on the top of the piston. There's also something that are called gas ports that can be in the piston, and they're typically located out near the edge of the piston, and those are to let combustion pressure pass through a little quicker to push down and generate pressure on that ring. Actually, the pistons I showed earlier had them. So you can see these holes in the top of the piston, those are the gas ports. So they're pushing, drilled all the way through into that top ring flange, so that it will pass the combustion pressure through. Now these are vertical gas ports. There's also a horizontal version that has like a half moon drill at the top of the ring. And you can also see here the horizontal ones for the oil ring that then put the oil into the inside of the piston here. So they're like throwing the oil out the inside to cool the bottom of the piston crown, as well as help throw some lubrication onto that wrist pin. Another feature that you can see on this particular piston is this additional groove between the top and the second ring. That one's an expansion groove. So it's up here, and it's just kind of cut in to be able to reduce the pressure between the second ring and the top ring to make sure that it doesn't build up too much pressure in this area that pushes back up to unseat the top ring. And that piston also had several grooves along the top edge up here that are there for helping hold maybe a little bit of oil and extra lubrication, but also, you know, having them grooves in there, it reduces the amount of surface area that might be dragging on the cylinder wall as well. And if you look closely at this piston, I don't know if you can see it, there's basically those same, there are larger grooves up on top there, but there's smaller grooves down along the side. That is not poor machining, that is done on purpose. And it is done on purpose to help hold a little bit more oil there to aid in lubrication. And while we're talking about that lubrication of the piston with the grooves, it's worth mentioning that that is what the crosshatch in the cylinder is for as well. That's what holds a little film of oil to lubricate that cylinder, because if it was glassy smooth, it wouldn't hold any oil at all, and it would cause quicker wear to the piston and the cylinder itself. Having a good proper crosshatch, it's actually kind of like mountains and valleys, if you will, or like a sawtooth kind of a looking thing. So the low spots hold oil and the high spots get knocked down during the honing process to make a smooth surface for the ring to ride back and forth on. But the low spots are there to make sure they're holding some lubrication. And if you've ever done like a dry versus a wet compression test, you know, having that oil there actually aids in compression as well as reducing the wear. Moving on for bearings, we already kind of covered that when we were talking about the crankshaft there. You know, you only get so many sizes for choices and trying to set clearances and stuff. Like, that's something you gotta plan for ahead of time if you're building an engine that doesn't have all of the options for bearing sizes. Now, I've also included the balancer and flywheel on here, and that's because of an external balance crankshaft. All that means is, you know, if we got our our crankshaft and it's internally balanced. The only thing we're balancing with is the crank itself. The balancer and flywheel are not going to have like weights added to them, versus if it's an external balance, they will have extra weights on them. There are certain years and styles of some engines, for sure on a Ford. I think even small block Chevy had some varying ones of the balancer size, where not only is it whether or not it's internal external balance, it's what size the weight is. So really that's something to consider. Now, why would you want internal versus external? Well, external was done just to add the weight to get the engine to balance out, instead of having to make a crankshaft that had bigger counterweights or be redesigned. You know, it was like maybe more of an afterthought kind of a thing. Not really sure how they ended up that way instead of just planning on it right off the bat. I'm sure it was probably cheaper to manufacture. That's why they did it that way. But things to consider as part of your short block, because you know, you need the rings, the bearings, rods, pistons to come up with a bob weight. And I haven't written wrist pins down because they're typically going to come with your pistons, unless you order them without, and I don't know why you'd bother doing that, but somebody might do it for some reason. But you need all those things come with a bob weight to then put on your crankshaft to spin it and balance it. And depending on where the balance is at, I mean, it'll be way off if it's supposed to be an external balance, or you're adding a ton of that expensive Mallory I was talking about to make it an internal balance, in which case you can ditch the weights on the balancer and the flywheel. So typically an internally balanced engine is better than an external balanced one, just because you end up with a big weight, and then the crankshaft, and then you got another big weight, so balancer, flywheel. The farther they are apart, the more of this you end up getting going on if it's out of balance a little bit. And that just creates bending forces in the crankshaft, versus if it's internally balanced, you've eliminated and moved all that stuff in by a few inches and made it just easier to balance. There's also a chance that the overall weight will be less, because otherwise, you know, the balancer's got to be built big enough, or built in a way that it can hold that big weight. And same thing with the flex plate or the flywheel, although it's typically much smaller because the distance is larger, the weight can be smaller. But just things to consider when you're going through your whole short block setup. Now, on my own personal engines, for a street application, I'm just going to be okay if it's already external balance. I'm just going to buy the stuff that comes off the shelf, external balance it, and it will be fine. Now, my race application, like the block I showed you earlier, that one is internal balance. It's also got a bunch of crazy other stuff like small block Chevy rods, custom pistons, you know, different stuff to lighten up a lot of those parts. But even when I went to an internal balance, I didn't get them light enough to not have to add a bunch of Mallory to the crank. And as I was talking about before, it gets expensive really quick. I think there was a few $100s worth of Mallory that had to go into that crankshaft in order to balance it out properly. So things to consider, because the flywheel and the balancer don't exactly get less expensive whether they have a weight or not. So, you know, and this all circles back to, you need to know what your goals are and your budget at the beginning of a build, because, you know, if I would need to budget for that extra cost of Mallory to balance out this crank, or it's probably only $50 difference in the balancer and the flywheel price about whether it's internal, external balance. You know, so there's a couple $100 difference that I'm saving just by being okay with it being external balance versus internal balance. And there are plenty of external balance engines that get raced. We're starting to talk, the more you bring all that stuff in, the easier it is on the components. So there's definitely, if you got a 6,000 RPM engine that you're also racing, external balance probably just fine. You probably don't want to be doing it on a 9,000, 10,000 RPM engine, and probably not even on an 8,000 RPM engine, because as you go up in RPM, all of the forces, you double the RPM, the force, or the effort that's being placed on that crankshaft quadruples every time you double the RPM. And that's why, when we balance out a crankshaft, we're getting down into like the sub 3 grams on a street application. On a race application, you probably want to be under 1.5 grams or a gram, because that's just spinning it at like, I can't remember, 500 RPM for the balancer to be checking the balance. Some balancers spin it a little bit faster. But now if you're trying to turn that engine, whatever RPM, say 5, so you double it to 1,000, double it to 2,000, double it to 4,000, double it to 8,000, like that's 5 times 4, so 20 times as much as whatever that imbalance was at 500 RPM. It adds up really quick. That's also why when we get into picking out components for our short block, weight is a big consideration for anything you're trying to turn RPM on. If it's a street car and it's just a cruiser, honestly, if you are even pretending to care, you're probably wasting your time. But on anything that you want to be hopped up and rotted on a lot, you need to start thinking about piston weights. And the big thing is, for a perfect example, this little piston and rod setup right here is my piston and rod combination for my 403 Oldsmobile that's now 463 cubic inch. We got a 4375 bore and still a 6-inch length rod. The difference is the stock rod was 780 grams. This one's 520. Now granted, it is a used NASCAR with a Honda rod journal. It helps a lot getting things small. It weighs a lot less. It's also a 780 pin instead of the stock 980. 990 is a big block Chevy. So the pins way smaller, so that makes that lighter as well. The pistons, the stock pistons were 740 grams. These ones are 560. There's just the wrist pin actually isn't that much different, because this one's actually a heavy wall turbo pin. Not because it's a boosted application, but just because that was what was suggested to me by the piston manufacturer when I spec'd this out. So the pin is actually fairly close to what the stock one was. It might still be, I think it's still around 20 grams lighter, but the bearings end up lighter, the bolts end up lighter, like the crankshaft itself got cut down for this lighter, the smaller pin. All in all, when it was said and done, the ring pack is like 40 grams lighter. And it's just kind of crazy how it all adds up. But when it was all said and done, the rotating assembly in this engine was 28 pounds lighter than stock. Now, we just talked about what a gram difference was, how you go from the RPM you're balancing it at 500 RPM to 8,000 RPM is 20 times. What do you think 28 pounds times 20 adds up to? Like, it's crazy. Not that it was an out of balance force, but that's still a force of 28 pounds that's changing direction every few milliseconds. It's crazy to think about the amount of stress difference that is. And the lighter the parts are, the easier it is on the other parts. The crank, the block, everything gets easier we circle that all the way back to our little demonstration with the inside mic and the block. You know, I pushed on it with whatever amount of force I was able to push on it to make that thing fall out. What do you think a piston going up and down in the cylinder is doing for force? It's a hell of a lot more than what I was pushing on it with. Now you bring that up in RPM and it starts turning into crazy numbers. Honestly, this is where you should really take a minute to appreciate that an engine runs it all, because the amount of just brute forces and chaos going on, it's amazing that they don't just explode at idle. It's crazy. It's crazy to think about. Another pretty cool way to think about that, or to visualize that, is it's an old sealed power video from the 80s. I tried to find it so I could put a link in the description, but I couldn't find it on YouTube. But I remember when I was going to school, we got showed this super old, it was on VHS. It was from the 1984 or something. Sealed Power had a video talking about some of this different stuff. But they had a short block, small block Chevy set up on just a hook to an electric motor so they could spin it over. It had perfectly flat top pistons put in it and no head on it. And if I remember correctly, they were turning it at 3,000 RPM. And this dude took a sharpened number 2 lead pencil and wrote Sealed Power in cursive on the top of that flat top piston while it was turning at 3,000 RPM, like it was a sheet of paper on a desk. 3,000 RPM, almost every engine in existence revs 6. Like, that's twice as much. And that piston is at top dead center like it's a sheet of paper. Crazy. Just crazy. Anyway, that's it for the short block video. Catch you next time with a new topic.